So, good evening, students. So, now we are continuing with the eigenvalue problem for free vibration analysis. In the last class, we saw some example also, how we can able to obtain the eigenvalue problem. And then we can solve for finding the natural frequency and the mode shape, and some physical interpretation of the mode shape. We saw how relative displacements among various generalized coordinate can take place for different natural frequency, and their shape is unique. So corresponding to one natural frequency, the shape of the mode shape is unique, and but the amplitudes are arbitrary. That is justified because it depends upon how much initial disturbance we are giving to the system. If it is vibrating with some natural frequency, so the same natural frequency can be excited for different level of initial conditions. So obviously the magnitudes of those response will be different all the time, but the relative shape will remain same. Today I will continue with the same eigenvalue problem, but today we'll take up another interesting system in which we can get the natural frequency 0 also, and such systems are called unconstrained systems. They are not constrained by the support, and that's why they can have natural frequency 0. And once they have natural frequency 0, that means there is no relative displacement among various masses, but as a whole, the whole mass can move. So let us see the slides. So I'll take up one example first for the previous eigenvalue problem, in which we had all the natural frequencies are low. So this is one example in which we have been given the mass matrix and stiffness matrix is given, but some of the elements are unknown in this. So, and the mode shapes for the eigenvector for the first natural frequency and the second natural frequency is given. In some practical applications, maybe this kind of requirement can be there, that we need a particular mode shape and what should be the stiffness of the system. Even the first natural frequency is specified, but second natural frequency is not specified. So some of the data are given, which in the form of the requirement of the mode shape and the natural frequency. So we need to obtain these stiffnesses to satisfy that the first natural frequency should be 50 radians per second. Corresponding mode shape is this, and the second mode shape we need like this. So this is 2 degree of freedom system. So the general eigenvalue problem we defined earlier like this. So here we can put the K matrix and M matrix. So this is the eigenvalue problem for this particular problem. So we have been given the first natural frequency. So first eigenvalue we can able to obtain by squaring the natural frequency, and corresponding mode shape is also given, eigenvector is given. So we'll utilize this information in the previous eigenvalue problem. So here I am substituting lambda 1 corresponding to the first mode, and then correspondingly this vector will be the eigenvector corresponding to the first natural frequency, this one. So this we have substituted for the first eigenvalue and the eigenvector. Now we can substitute value of the lambda 1 and the given mode shape here. And then if we simplify this, because these are numbers and some unknowns are there, so this can be clubbed like this. Even we can able to expand the first equation, because this is a matrix form. There are two equations. So first equation will give k1 is equal to 0. Second equation will give this into 1 and this into 2 is equal to 0. So from here, because k1 is 0, k2 can be obtained. So now with the information of the first natural frequency and the first mode shape, we could able to get the stiffness k1 and k2. And still we don't know the second natural frequency, because in the problem second natural frequency is not there. So we need to find out the natural frequency associated with this. So again we'll write the eigenvalue problem now for the second eigenvalue lambda 2, and this will be correspondingly eigenvector. So now because lambda here k1 k2 is now known, so that can be substituted, and the eigenvector here also can be substituted, and if we simplify we'll get something like this. And you'll see that from the first equation or the second equation we are getting basically the same value of the lambda 2, that is 2500, and from there we can get the natural frequency if we take the square root of this. So it turns out to be that both the natural frequencies are same here, because the first natural frequency was also 50 Hertz. So basically if you see here, when we substitute the k1 and k2, the mass matrix and the stiffness matrix off diagonal terms are 0, so that means they are uncoupled basically. So the choice of the eigenvector which was given makes the system uncoupled, but if the different eigenvector we could have chosen in the first case, we could have got the coupled system. But for this particular case, they are uncoupled system, and both the natural frequencies as same for this. So this is one example. Now I'll take up some property of the eigenvector. I define the orthogonality condition. That means the two mode shapes, they are orthogonal to each other. And now I'll be proving that particular orthogonality condition. So this eigenvalue problem we can write for rth mode. So you can see when I'm saying rth mode, the natural frequency is omega r, and eigenvector is also having subscript r. The same equation should satisfy the any other mode also. So if I'm saying the sth mode, then if we put the corresponding natural frequency in this eigenvalue problem and corresponding eigenvector, then also it should satisfy, because this should satisfy for all the eigenvalues and corresponding eigenvector. So once we have this, now what we'll do, we'll multiply the first equation with the mode shape of the eigenvector sth, that is transpose of that, and the second equation will multiply by the rth eigenvector transpose of that. So if we multiply it, we will get this equation. So both sides we are multiplying by the transpose of S in the first equation, and in the second equation both R transpose, UR transpose we are multiplying. Now Now what we are doing, we are subtracting one from another, and noting that the mass matrix is symmetric. So if you see here, R is here, S is here, and because of the symmetry, even if we swap the superscript S and R, these two will be same because mass matrix is symmetric. Same thing will be valid for the stiffness also. So that means if you see here, here, and here, basically this matrix, this multiplication and this matrix application will be same according to this because mass is symmetric. Similarly, this right side term in the first equation and the second equation also will be same. So if we subtract one from another, this will be common. So here omega r square minus omega s square, and one of them we can take. So this is, I'm taking common. And right side, because they're equal, that will give us 0. Because right side this condition is there, so that will equal to 0. Now, if you see here, because we have taken two different natural frequencies, and in general, two natural frequencies cannot be equal. So if they are equal, then only this will be 0. But for general case, they cannot be equal. So that means this we cannot equate to 0. If this is not 0, then we must have the other three terms equal to 0. So that means if we equate this equal to 0, we'll get a condition. And that is the orthogonality condition, that when we have the sth eigenvector and rth eigenvector, and in between the mass matrix, this is 0 when r is not equal to s. And we have seen that when both are same, that is the way we normalize the mass matrix. So we equate that equal to 1, but when they are different, then is 0. And this is the statement of the orthogonality condition. So here you can see once this is 0, if this is 0, then if you substitute it here, because this is having some value, so this also should be 0, because once this is 0 for r not equal to s, so if you substitute here, this also term will be 0. So this is that particular term in which the stiffness, with respect to stiffness also, if this two eigenvectors of different modes will be orthogonal to each other. And as I mentioned previously, it is true only when the M and K are symmetric matrices, because when we subtracted one equation from another, then we could able to cancel some of the terms to get this particular condition. Okay, so yeah, so this is the same thing, which I think here K also symmetric. In case when there are repeated roots, sometimes in this specific case we may find that two eigenvalues are same. So in that particular case, the corresponding eigenvector may not be orthogonal, but we can able to make them orthogonal by some linear combination of these two eigenvectors. So that case we'll see separately. So when we, as I mentioned, when we have the same eigenvector, then we get some non-zero values. So let us, I'm representing that as MRR. And here eigenvectors are not mass normalized. So we'll not get 1 here, we'll get some value. Similarly for stiffness, if we take the same rth eigenvector either side, we'll get some value, that is KRR. So if we take all the modal matrix So this is for one of them. So if R can vary from 1 to n, so all such R, that is M11, M22, Mn, all those will be coming in a form of matrix in the diagonal term. So here only single vector is there, but here whole model matrix is there. That means all eigenvectors are combined for R is equal to 1 to n. So we'll get a mass matrix diagonal, and similarly the stiffness matrix diagonal. And here whatever the eigenvector have been used, they are not mass normalized. If we are using mass normalization vector, then we will get the mass, this as identity matrix, and this will be the square of the natural frequency in the diagonal terms. So this we already seen in the example also. So this is the orthogonality condition, which is very useful, but this is valid for the symmetrical mass and stiffness matrix. So extension of this is the expansion theorem, in which we obtain the various eigenvectors corresponding to the each eigenvalues. So u1, u2, u3, all these are the eigenvector corresponding to the eigenvalues. And we have seen they are orthogonal. That means they are independent of each other. And basically this is a basis for obtaining any response of the system. Like here represented, x is the generalized coordinate of the system. So we have n degree of freedom system. So n generalized coordinate will be here. So that response can be obtained by summing up all these eigenvector multiplied by some constant. There are n eigenvectors, so summation is that. And this CR will depend upon the initial condition. So it depends upon the initial condition, which particular eigenvector will contribute to the total response. But any general response can be generated using this, and this is the nothing but the expansion theorem, similar to the Fourier series. But here, instead of harmonics, we are using the eigenvector of the system multiplied by the some constant, and this constant can be obtained if we pre-multiply this equation by transpose of U and M matrix. So if you multiply this, we'll get this is the multiplication of this. This side also we are multiplying the same U transpose and M. Now, if you see, this remains same here because this is a series. Okay, this is a series. So if you see U raised to R transpose M, and this is a constant. Constant will come out. There's no problem. That means that will not be in between the two matrices. It can come here. So this quantity U R transpose M and U R. So R can vary from 1 to n. If R is 1, this will be U1. So U transpose T M U1 will be 0 according to the orthogonality condition, because when these two modes are different, then with respect to the mass or the stiffness, using the orthogonality condition, this will be 0. Even for R is equal to 2, it will be 0, 3. Only when R is equal to R, then this will be having, so here it has been shown, when R is equal to R, then only it will be non-vanishing. Otherwise, all the terms in the series will be 0. So for R is equal to R only, this will be 0, will be having some value, otherwise it will be 0. And when we mass normalize it, then this quantity will be nothing but the identity matrix. Because now you can see this is the identity matrix, because both are UR, and so identity matrix. So from here you can get the CR. So CR is equal to this. So this is the constant which we need to find from the initial condition of the problem. So X will contain the initial condition of the problem, and depending upon that, CR can be obtained. And if you substitute here the response at any time, we can able to obtain. in which the contribution of the various modes will be there, and the contribution, how much is there, will depend upon the CR, which again depends upon the initial condition of the problem. Okay, so this is using the expansion theorem, we obtain the response of the system, and this the orthogonality conditions is being used. So this is called modal analysis also. Okay, so now I'll take up the semi-definite system or the unconstrained system. I'll take the questions at the end. So let me start this. So semi-definite system, we have seen that the positive definite system. Positive definite system is in which the kinetic energy is positive definite and potential energy is positive definite. But semi-definite system, now let us see what is the thing. So here this is the kinetic energy expression, potential energy expression. We are assuming, sorry, this should be okay. Yeah. So M and K, we are taking symmetric till now. And kinetic energy is always, because mass matrix is always positive definite, because kinetic energy becomes zero when there is no velocity. So mass is always positive definite. Now we are considering a system in which the potential energy is zero when without the motion being zero. That means the potential energy is zero when while there is a motion. While there is a motion, potential energy is zero when there is a motion also. So such a system in which we have the potential energy zero when motion is also taking place, that particular K matrix will be called positive only. But minimum potential energy for that will be zero only. Even that means if the displacement is taking place, the potential energy can be zero apart from the at its equilibrium position or static position. So this system is called only the positive. This matrix is called positive, and such system in which the M matrix is positive definite and K is only positive, then it is called semi-definite system. And in such system, the potential energy does not correspond to always the equilibrium position. So that is the case. So one such system is shown here. You can see that this wagons are moving in horizontal motion. And if you see, none of the wagons are attached to some fixed support. They are moving on a rail, but they are connected with each other, but they have not been connected to some fixed support. So as such, they can move anywhere without any problem. So such system is called unconstrained system, in which none of the masses are attached to some fixed system. They are connected by each other only. So for such system, so this is the eigenvalue problem which we have been talking about. So sometimes we use here lambda, or sometime omega square, they are one and same. So if we pre-multiply this by U transpose, we will get this, because omega square is constant. This we can keep at the front. So now if you see, so this is the eigenvalue problem, and we have just pre-multiplied by this. Now we are thinking of a column matrix which is making the system. So this is the displacement we are giving, or this is the this is the displacement we are giving, which is making the system the potential energy 0. So that means there is a displacement in the system, but that is making the potential energy 0 even the displacement is taking place. So that is the thing we were talking about in the previous slide, that when displacement is there, then also the potential energy can be 0. So such system is semi-definite. So we are considering that, let us say U naught is a displacement which is making the potential energy 0. So if we put this here, so every U I am replacing by U naught. Okay, so now you see, because what is this quantity? If I add half here, this will be nothing but the potential energy corresponding to this displacement. So according to this condition, that the potential energy is 0, because we are assuming that this is the displacement which is making the potential energy 0. So this term should be 0. So if we equate this equal to 0, we'll left with this equal to 0. So this is the thing. And here omega has been replaced by omega naught, corresponding to this particular displacement. Now, in general, this particular quantity with the mass matrix multiplied, it cannot be 0 in general. Okay. So if this is not 0, so only possibility there, omega is 0. Omega naught is 0. So that is the so such motion is possible only when the natural frequency is 0. So whatever the motion we are thinking about, which makes the potential energy 0, is possible only when we have the natural frequency 0. And this is the characteristics of the semi-definite system, that at least one of the eigenvalue will be 0. Sometimes maybe two eigenvalue can be 0. And this U naught, which we assume, is called the 0 mode. And often this is called rigid body mode. Through one example, we'll see what is the rigid body mode. Basically, rigid body mode means all the particles are moving together with the same displacement. So that is, even they have flexibility in between, but they are acting as a rigid body and moving simultaneously in same direction. So this is the condition we got, that one of the natural frequency should be 0 for such semi-definite system. So I'll take up one example of the unconstrained system. So same figure is there in which we started with. So here three generalized coordinates are there, x1, x2, x3, and in between there are stiffnesses k1, k2, and masses are this. So we are assuming that this particular body is moving in a horizontal direction. The vibration is taking place in the horizontal direction. So we can write the kinetic energy of this and potential energy of this, because this K1 is having displacement x2 minus x1, and this K2 is having displacement, the extension K3 minus K2. So that potential energy is there. And once you know the kinetic energy, potential energy, the equation of motion can be obtained, and this is the mass matrix, this is the stiffness matrix. And it has been shown that how this can be expressed in terms of the general expression which we have been using for kinetic sorry, this is all derivatives should not be there here. Let me remove it. Because these are potential energies, so derivatives will not be there. Only the okay. So this is the quadratic form of the potential energy we have been talking about, and the quadratic form of the potential kinetic energy we have been talking about. So the x is representing the vector of the velocity transpose of that. So if you multiply, you'll get the kinetic energy, and the potential energy. So once we have the mass matrix, stiffness matrix, now we are considering a situation in which, let us say, all the three masses are having same displacement. So if all three masses are having same displacement, what will happen to the potential energy? Because x2 is equal to x1, so this quantity will be 0. x3 is equal to x2, this quantity also will be 0. That means potential energy is 0. So this is the condition which we have been talking about for semi-definite system, in which the system is having displacement. So all these three masses are having same displacement, x0, x0, x0. So these springs are not getting stretched. So potential energy remains 0 even when there is a motion of these three. So this is the condition. This is the displacement which is making the potential energy 0. Even the system is not in equilibrium because we have given some displacement. So initially equilibrium position got disturbed, and still the potential energy is 0. And you can see that this is, even the springs are there, they are not getting extended. That means the whole system is moving as a rigid body without any extension of the spring. As a whole, they are moving as a rigid body. So this is called rigid body mode, and we'll find that the corresponding natural frequency will be 0. It will not oscillate. It will move in one direction only. Okay. Okay. So this particular x0, which we are talking about, the rigid body mode, and so this is the orthogonality condition we are writing for. So if this is a different mode, and this is the rigid body mode. So according to the orthogonality condition, because they are different mode, this should be equal to 0. So once it is 0, because this two matrices, if you multiply, we'll get this m row vector. So if we multiply these two, we'll get m1, m2, m3 as a row vector. X will remain as it is as a column vector. And if we multiply this again, we'll get this condition, m1 x1 plus this. So this is we are getting from the orthogonality condition of the rigid body mode with any other mode of the system. If we differentiate that particular equation, previous equation, with respect to time, this can be expressed like this, which is representing that the linear momentum for such unconstrained system, so having elastic motion, longitudinal elastic motion with no external force applied, must be 0. So linear momentum of the system is 0, is indicating. And if we want to go back by integrating this and coming to this, only thing we need to see that the initial condition which we are satisfying, this will be the initial condition we need to satisfy if we want to go back from here to there, which represent that the center of mass of the system should not get disturbed if we want only the elastic motion to be taken place. If we have rigid body mode along with the elastic, then the center of mass can shift. But if we want only pure elastic motion, then the center of mass of the system should not change. Now, from the previous equation, this condition which we got from the rigid body mode, which is present in the semi-definite system, this can be expressed. Basically, this is giving a relationship between a x1, x2, x3. So as such, you can see x3 can be expressed in terms of the x1 and x2, or any other. So if we know x1 and x2, we can get the x3 from here. So this equation I have written like this, so that Okay, so x3 is this. Now I'm using identity x1 is equal to x1, x2 is equal to x2, and now I'm combining these three equations in one. So three equation in one, x1, x2, x3, x1, x2, x3. So if you see first equation, x1 is equal to x1. If you multiply, x2 and x3 will get 0. So x1 is equal to x1. Second equation is x2 is equal to x2. And third equation is which we got from the orthogonality condition of the rigid body mode. So third equation will be this. So the first equation, second and third, they have been combined here. Now, because if you see this last column is all 0, so that means they are getting multiplied by x3. So x3 will not contribute. So if we eliminate this, we'll get x1, x2, and this will remain same. That last column we have removed. So that means is giving some kind of transformation from x1, x2, x3 to this, because x3 is related with x1 and x2. So there is no need to solve the eigenvalue problem with all three. Only two is enough, and then x3 can be obtained from this relationship. So C is the some kind of constrained matrix, we can say. This is some kind of transformation we can use. So here that previous equation, this is having 3 by 1 size, this is 2 by 1 size, so x1 and x2, and C is the matrix which is relating this. If we take the differentiation with respect to time, because C is constant, if we take transpose of this, they will swap, and then transpose of this will be there. This will be using in the kinetic energy. So kinetic energy initially we had in terms of the three generalized coordinate. So we are replacing that with two generalized coordinate. This is similar to the transformation which we have been using. So you can see now the C transpose MC I'm combining as a M prime matrix, and this will be 2 by 2 size matrix. Earlier M was 3 by 3 size matrix, and X vector will be again 2 by 2 into 1. X1 and X2 will be there. Similarly for the potential energy, this can be written as K prime. So M prime and K prime, the new transformed equation matrices we are getting like this, which will be 2 by 2 symmetric matrix. So eigenvalue problem is this now. So instead of M and K, we are using M prime and K, which is having one uh, the size of the matrix is less by one column and rows. So and X is here only X1 and X2. So from here we can get two eigenvalues, because now as we have been doing previously, with that we'll be having the, because size is 2 by 2, so we'll be getting the two natural frequencies, and corresponding eigenvector also we'll get x1 and x2. The size of that will be 2 into 2, 2 into 1, and but actual system is having x3 also. So this eigenvector, once we obtain, we can get the total x1 and x2 using the transformation again. So you can see using this transformation, this 2 into 1 matrix. So if you multiply, we can get the x1, x2, x3 here. Similarly for the second mode. And rigid body mode, we know that is natural frequency is 0. And so along with the omega 1 and omega 2, we'll be having omega naught, that will be equal to 0. So three natural frequency, one will be 0, another will be omega 1 and omega 2. And eigenvector like this. So this is one of the example I took. That was the a equation of motion. This is a 3 by 3 matrix. So you can see mass matrix is given by this, stiffness matrix is given by this, and eigenvalue problem problem. If we combine this, we get like this. Now we need to obtain the non-trivial solution of this. So we need to take the determinant of this equal to 0. So if we take determinant of this equal to 0, we will get some polynomial. So polynomial can be rearranged and put in this form. So we will get one of the eigenvalues 0, another 1, another 3. So 3 eigenvalues we got it, and they're having these values. Natural frequency is related with the eigenvalue is the square root of this. So lambda, I think I defined here. So that can be used to get the omega square. So I'll get the kt by ip, and third I can get this because 3 is here. So I got the 3 natural frequency. Eigenvector also we can get using whatever the procedure we followed. I'll give one case here. So eigenvector for, let us say, 0 natural frequency first. So this is the eigenvalue problem in which I'm putting the lambda 1, which is 0. So if we put lambda 0, I'll get this. Now, because there are three equations and 3 unknowns, and they are homogeneous, so we cannot solve them uniquely. But again, we'll try to find out the relative displacements of these. So if I take the first equation, theta 1 minus theta 2 is equal to 0. Here, if I take the third equation, then because here is 0, so our relations will be simpler. So I took the third equation. So this is theta 2, why it is coming like this, theta 1. This should be 1, I think. Let me check. Yeah, here is 1 actually. By mistake, I think that has been. So this should be 1. These are 1. So then our equations are fine. So now you can see minus theta 2 and theta 3, this equation. So from first equation, I'm getting theta 1 is equal to theta 2. From second equation, I'm getting theta 2 is equal to theta 3. That means theta 1 is equal to theta 2 is equal to theta 3. So there is we got three relative displacements, and here if I want to use the transformation, so this transformation can also give the same thing, but at present I have not reduced the system to 2 by 2, so this may not be needed at present. Okay, so if I so this is, I think, C matrix. So now you can see that I have shown one of the lambda is equal to 1. I have shown the how to get the eigenvector. So this is 1, 1, 1. So if theta 1 is 1, theta 2 is also 1, theta 3 is also 1. On the same lines, the second column can be obtained corresponding to second natural frequency. Third column can be obtained using the third natural frequency. So that I am leaving it to you to obtain the corresponding to this and this using the same procedure up to this. Now I'm using the transformation to reduce the 3 by 3 size matrix to 2 by 2, because this is a rigid body mode is there, so we want to eliminate that. So this is the transformation matrix C which we found earlier. So this transformation matrix I am using in the original mass matrix to get the reduced size of the mass matrix 2 by 2. So this is the original matrix. If I multiply the transformation matrix, we'll get the reduced mass matrix like this. Similarly, the reduced stiffness matrix like this. And now we'll form a eigenvalue problem for this smaller size matrix. And if we combine this, we'll get this. So determinant of this will give again the same eigenvalues. Not the zero we'll get from this, because we during the transformation is already assumed that it is having zero natural frequency, so that has been eliminated, and the calculation will be simpler because 2 by 2 matrix. So lambda 2 and lambda 3 we'll get from this. We'll get the same value. Now, okay, so so using that adjoint matrix, how we can able to get the eigenvalues, I will just eigenvector, I will explain. So here, this is the eigenvalue matrix, eigenvalue problem matrix. So first I'm solving for the lambda 1 is equal to 0. So previously I solved the eigenvector using conventional technique, this procedure, by expanding and other things. So here I'm giving one example how the adjoint of matrix can be used to find the eigenvector. So for lambda 1 is equal to 0, if you put here, I'll get the A matrix. So this is the A matrix. Now adjoint of this I need to find out. And we already seen that the adjoint of the matrix small a will give us the eigenvector that will be proportional to the eigenvector. So adjoint of the matrix is defined like this. So here M is the minor determinant. So if I'm saying A11, so that means I need to eliminate the first row and first column of the original small a matrix. So here, if I eliminate the first row and first column, I'll be left with 2, 1, minus 1, 1, this. So determinant of this, so minor, so is nothing but the determinant of that minor. Here ij is 1, 1, and this sign ij is 1, 1. So this will be positive, and determinant of this will give us 1. So A11 is 1, which is the adjoint of the matrix A, the first column. So if you see here, I have obtained this one, A11. Now I want to find out the A12, because this is first is the row and second is the column, and I think yeah. So if I put 1, 2, that means first row and first row 1, 1. Okay, so second row, this should be, I think, 2, 1. Let me write, I think this subscript 2, 1, and this will be 3, 1. I'll explain what is the subscript means. Subscripts are basically the first subscript represent the row and second column. So when I'm saying second row and first column to be eliminated, so that means from this second row and the first column, second row and the first column. How it is giving 2, 1, minus 1, minus 1, second column.
Sir, it was correct before.
Okay. I think is okay. Row.
The transpose is taken in.
Okay.
That.
Where? Oh, transpose is taken. Oh, sorry. Here again, the transpose is there. Okay. So that is the we missed. Okay. So I think 1 2 is okay. 1 2 is okay. 2 1 is okay. Yeah, fine. So MJ. So MJ is what? I think I messed up here. Basically is giving this. What is giving? Yeah. So I have eliminated here basically the first row and the second column. No, first row and second column. First row and second column. Yes. So this should be same. I think that's fine. So if you see, first is representing the row, second column. So if we remove the first row and second column, I'll get -1, -1, 0, 1 is fine. And if I take this, then this will become 1. Similarly, this is 1, 3, first row, third column to be eliminated. So first row and third column, so -1, 2, 0, -1. So this. So basically, I obtain the first column of this. If I obtain the second column also, that will also be same or proportional to the first column or third column. So the adjoint matrix is basically, you will find that you take any of the column that will be proportional to the eigenvector. So this is the rigid body mode. So rigid body mode, you can see that we have first all three disks are having same, or this all the wagons are having same moment. So 1 1 1. The same thing we can able to repeat for the second eigenvector, and in that you'll find that there is need to find out one of them, others will remain same. So I'll explain the graphical representation of this. So this is the eigenvector. So you can see that the first is having -1 displacement. Other two wagons are having 1 1 displacement. So these two are having similar motion, but this is having opposite motion. And if I take the third eigenvalue, procedure remain the same. We can see that this particular thing, first and last will be having same direction motion, and the middle one will be having opposite. So if he's moving in the right, this is moving in the right, this will move in the left side, but the displacement will be twice of this two. So, and here also you take any column, all the column of the adjoint matrix of this corresponding to the lambda 3 will give us the eigenvectors. So this is generally good for programming purpose, so that you can directly get this kind of eigenvectors. So I'm stopping here, and maybe I'll take up some more example in the next class. If you have any query on this, you can ask any query from today's lecture. So this adjoint matrix thing is basically because we'll be dealing with in the present course maximum 3x3 matrix. So even by hand calculation, by expanding the equation, they can be obtained. But for programming purpose, if you are interested in, then that can be adjoint matrix procedure can be used. So Sai Guru.
Today I explain one example now, sir. 4.2 in starting.
Hello.
Hello, sir.
Ha.
Today in the starting I explained one example 4.2.
Yeah.
In that, for same lambda value, we are getting two mode shapes.
4.2.
Starting, sir.
Yeah.
For same lambda value, we are getting two mode shapes.
Yeah, actually, what is happening here, the mode shapes are independent. Actually, if you use any other mode shape, also you'll get the same. So actually, this is independent of the mode shape, the second one. have written here. Mode shape have no meaning actually here, because the two systems are uncoupled, so they cannot have relative motion.
Okay, so
Two systems are independent, is something like that.
so that relative displacement will have same ratio does not hold here.
Yes, because both the systems are uncoupled.
Okay, okay, sir.
So
Thanks, sir.
if we could have chosen some other mode shape here, I think then we could have got some, because here we are getting K1 0. So if we are not getting K1 0, then if you see, we got the K1 0. So what is happening? Mass matrix is diagonal. Stiffness matrix was anyway, sorry, this is stiffness matrix is diagonal. Mass was anyway diagonal. So both got diagonalized.
Okay.
So for if we could have taken some other mode, then K1 if is not 0, then the natural frequency will not be same. Okay.
Yes, sir.
Yeah.
Okay, sir. Thanks.
Yeah. Any other question? Any other question? So I have already given this, I think, fourth assignment related to the eigenvalue, eigenvector. So you proceed with that. If in some of the examples the numerical values are not there, maybe you can assume some realistic value, or you can take feedback from me. And I think also I announced the second quiz on 17th, so that because we need to take 4 to 6 quizzes. So I'm not sure whether we can go up to 6, but at least 4 to 5, if we can take, that will be good enough. So I think if there's no question, then I'm stopping here.